Understanding the structure of the atomic nucleus is one of the central challenges in nuclear physics. Nevertheless, it is given by the amount of energy contained in the gluons. This energy dictates the separation between subparticles inside the hadrons, protons and neutrons, and so the charge for the protons and leptons, in this case the electrons, and therefore their distances to the nucleus. Yet there are several orbital distances for the electrons. This is given by the fact that gluons in the hadrons can indeed absorb energy from the leptons, but not every bit, so basically those with the lowest energy stay at the first orbital as consequence of the pull for energy of the hadrons, and so the higher the energy, the higher the orbital occupied. Remember, even leptons in the outer orbital can lose enough energy to the hadrons that they can drop to a lower orbital, while others, by absorbing external electromagnetic radiation, can go up the ladder. The last orbital or shell, for any given atom, is called the valence shell. Leptons here are the ones that are capable to form molecules with other atoms of the same element or another. As atoms struggle to reach a balance in the valence shell of 8 leptons, they pull each other in an energetic dance, trading electrons until the balance is reached, by any means necessary. These are the famous chemical bonds, ionic, covalent and metallic. For example, sodium has a valence shell of 1 electron with an underlying orbital of 8, while the chlorine has 7 electrons in the valence shell. By an electrifying ionic dance, the sodium atom leases its 1 electron to the chlorine, and by doing so, the sodium underlying orbital is now the valence shell with 8 electrons, and for the chlorine, the valence shell has been completed to 8 electrons, reaching the perfect balance for the molecule called sodium chloride, commonly table salt. Basically, for every molecule, as for the interior of the hadrons and leptons, the structure is given by the repulsion and attraction of the nuclear force, and its strength given by the number of hadrons and leptons present. Density is a curious case nevertheless, as higher density is not given by the number of hadrons and leptons alone, the subatomic structure of quarks and neutrinos, and the stable energy quanta for the gluons inside them, can give more density at lower weights. So, which is your favorite bond?